In this video, we are going to go through all the problems in homework 13. In this homework, we totally have 7 problems. The first 3 problems are about similitude, and the remaining 4 problems are about dimensional analysis. Now let's take a look at the first one. In this problem, the oil flows through a smooth pipe. We know the kinematic viscosity of the oil is 4 times 10 to the power of minus 6 meters squared per second. The diameter is 15 centimeter. The velocity of the oil is 3 meters per second. And we want to know what velocity should water at 20 Celsius degree in a smooth pipe 5 centimeter in diameter to be dynamically similar. So when the temperature is 20 Celsius degree, we can find its corresponding kinematic viscosity of the water. It equals to 10 to the power of minus 6 meters squared per second. So we want to identify the velocity of water, which is V2. Since this is like flow in a smooth pipe, there is no compressibility effects, the free surface effects, and gravitational effects. So the only pi group that is appropriate is Reynolds number. So the dynamic similarity is achieved when the Reynolds number in the first pipe it equals to the Reynolds number in the second pipe, right? So the Reynolds number it equals to the velocity times the diameter divided by the kinematic viscosity. So we want to identify the V2 here, right? So we put the V2 to the left-hand side. V2 should equals to V1 times D1 divided by the kinematic viscosity and times the kinematic viscosity of water divided by the D2. So we can bring the value here to this equation. The V1 is 3 meters per second and diameter is 0.15 meter. And kinematic viscosity of the oil is 4 times 10 to the power of minus 6. And then we times the kinematic viscosity of water is 10 to the power of minus 6 divided by the diameter 0.05 meter. So in the end, we can get V2 it equals to 2.25 meter per second. So this is the result for the first problem. Now let's take a look at the second problem. In this problem, there is a large venturimeter is calibrated by means of 1/10 scale model using the prototype liquid. So we can know that the Lm divided by the Lp it equals to the 1/10. So the first question is, what is the discharge ratio for the dynamic similarity? And the second question is, if a pressure difference of 400 kilopascal is measured across ports in the model for a given discharge, so what pressure difference will occur between the similar ports in prototype for dynamically similar conditions, which is delta P in the prototype? And because it is the same liquid, so we can know that, we assume that the viscosity in the model it should equals to the viscosity in the prototype, same to the density. And in this problem, it's similar to the first problem, which is there is no the compressibility effects, the free surface effects, and the gravitational effects. So the Reynolds number is the only significant group. So the pressure coefficient should equals to the function of the Reynolds number. So to solve this problem, first, we need to equate the Reynolds number to find the velocity ratio and then to find the discharge ratio. So the Reynolds number in the model should equals to the Reynolds number in the prototype. And then the Reynolds number, it equals to the velocity times L divided by the kinematic viscosity. So we do the same stuff on the right hand side. And based on that, we can know that the ratio of the velocity should equals to Vm divided by the Vp. It equals to Lp divided by the Lm times the viscosity ratio. And because we know that the viscosity is the same, right? So it should equals to 1, then we know that the velocity ratio should equals to the ratio of the length. So it equals to Lp divided by Lm. And then we can determine the discharge ratio. Discharge ratio, it equals to the velocity ratio times the area ratio. So it should equals to, because we know the velocity issue is here, right? So it equals to Lp divided by Lm times the area ratio, it equals to Lm divided by Lp to the power of 2. And then after we calculate this equation, the flow rate ratio, it should equals to the Lm divided by Lp, which is given, so it equals to 1/10. Now we solved the first question. So the second one, we want to find the pressure by equating the pressure coefficient, right? So the pressure coefficient in the model should equals to the pressure coefficient in the prototype. So the pressure coefficient it equals to delta P divided by the density times velocity square. This is for the model. And this is for the prototype, okay? Because we want to know the delta P in the prototype, so we put it on the left-hand side. So the delta P, it equals to delta P sub m times the density ratio times the velocity ratio to the power of 2. And then because we know that the ratio of velocity, it equals to the ratio of the length. So it equals to LP over, so it should equals to LM divided by LP to the power of 2. And then we can bring the value to this equation. The delta PM is 400 kilopascal. And the density ratio, it equals to 1. So we times 1. And the length ratio, it is given here, right? So it's 1/10 to the power of 2. Okay, so we can know that the pressure difference in the prototype, it should equals to 4 kilopascal. This is a second result for this problem. Now let's take a look at the third problem. In this problem, there is a 1/25th scale model of a spillway is tested, which means that Lm divided by Lp is 1/25. And we know the discharge in the model is 0.1 cubic meter per second. So the first question it asks us, to what prototype discharge does this correspond? Which means we need to determine the QP. And the second question is, if it takes 1 minute for a particle to float from one point to another in the model, how long would it take a similar particle to traverse the corresponding path in the prototype, which is T sub p here? So let's solve the T sub p. So we know the time is involved in the velocity, right? And because it is a spillway in this problem, so we need to which means that it's like gravitational force dominated. Therefore, we need to matching the Froude number first. So the Froude number should be the same in these two situations. So the Froude number in the prototype should equals to the Froude number in the model. The Froude number, it equals to the velocity divided by the square root of gravitational acceleration times the length. So it should be the same on the right hand side. Okay, so in this case, we want to find the velocity ratio, right? And the acceleration should be kept the same, right? And then we can know that if we put like Vm on the left hand side, which is Vp over Vm, the ratio, it should equals to the square root of Lp divided by the Lm. Okay, so we know that the Vp divided by the Vm it also equals to the Lp divided by the Tp, and then divided by the Lm divided by the Tm, right? So based on these two equations, we know that Lp divided by Tp divided by Lm divided by Tm should equals to the square root of Lp divided by the Lm. And then based on that, we can identify the ratio of the time, which is Tp divided by the Tm. We put the Lp divided by Lm on the right hand side, so it equals to Lp divided by Lm times Lm divided by Lp to the power of 0.5. Okay, so we know that Lp divided by the Lm is 25, right? So the Lp and we know the time, the Tm here, it equals to 1 minute. So we can put the Tm on the right hand side, right? So after we bring the value to the equation, we can get Tp it equals to Lp divided by Lm to the power of 0.5 and then times Tm. It should equals to square root of 25 times 1 minute, right? So in the end, we get Tp equals to 5 minutes. Okay. This is the first question. The second one, it asks us to identify the QP. Okay, So the QP, the ratio of the discharge, it should equals to ratio of the length to the power of 3 divided by the ratio of time. Right? And we know the ratio of time it should equals to here. Based on this, we know the ratio of time should equals to the square root of the ratio of length. Okay, so we can bring this equation to the first one, then we can get the ratio of discharge. It should equals to LP over LM, the ratio of length to the power of 2.5. And then because we want to identify the QP here, so we put the QM to the right hand side, and then we can get QP equals to LP over LM to the power of 2.5, then times QM. And we know the ratio, the LP over LM should equals to 25, right? Is provided. And we know the QM. Here it equals to 0.1 cubic meter per second. Then we can get the QP should equals to 312.5 cubic meter per second. Now this is like complete result for the third problem. Now let's move on to the problem 4. In this problem, it provides us two different equations. It wants us to identify if these two different equations are dimensionally homogeneous or not. So if the equation is dimensional homogeneous, it means that the power of dimensions on the two sides of the equation, it should be the same, right? So let's take a look at the first one. So on the left-hand side, it is Q. So the dimension of the discharge, it should equals to L to the power of 3 over T. And we call it equation 1. And then on the right-hand side, we know there is 2/3 times C. We know the C is a pure number, so the dimension of this part for a pure number, it equals to 1. And then the L, the dimension of L is L itself. And in the square root is like 2g, right? So because we already know the dimension of this like pure number, 2 is 1, so we just ignore it. So this should equals to L over T squared to the power of 0.5. And then the dimension of head, it should equals to L to the power of 3/2. And then we know that the dimension on the right hand side this part should equals to is 1 times L times G is L over T squared to the power of 1/2 times L to the power of 3/2. So in the end, we will get that it should equals to is L, these two cancel out, so L to the power of 3 over T, right? So it is equation 2. And because we know these two are the same, so we know that the first equation is homogeneous. This is a result for the first question. Now let's take a look at the second one. On the right hand side is like velocity, right? So the dimension of the velocity is L over T. We call it equation 1. And on the right hand side, it is 1.49, which is pure number. Its dimension is 1, so we ignore it. And then it's like 1 over n. We know that n is length to the 1/6 power, so its dimension should equals to the L to the power of minus 1/6. And then this R is the length, right? So the dimension is equals to L, but we need to pay attention, it has a power, which is 2/3. And then the S is a slope. Power is 1/2. So because like the slope, the dimension of the slope, it should equals to 1. So it will be 1. If we combine these 3, we know that on the right hand side, 1.49 over n times the length is 2/3 times the slope, to the power of 1/2 should equals to this L to the power of -1/6 times R is L to the power of 2/3 times the slope is 1, right? And then we got it should equals to L to the power of 1/2. This is our second equation. So we know that the equation 1, it doesn't equals to the equation 2, right? So for this case, we know that this equation is not homogeneous. This is a result for the second question. Now let's move on to the problem 5, 6, 7. This 3 problem, when you solve it, you can choose either the step-by-step method or the explanation method. So for the problem 5, which is problem 8.8, I will use both methods to solve it as a demonstration. But for the problem 6, I will use the step-by-step method only, and for the problem 7, I will only use the explanation method. Now let's take a look at the problem 5. So in this problem, we know for very low velocity, it is known that the drag force of a small sphere is a function solely of the velocity of the flow past the sphere, the diameter of the sphere, and the viscosity of the fluid. It asks us to determine the pi groups involving these variables. So let's solve this problem using the step-by-step method first. Okay, so the first step is to list the dimensions of significant variables. There we have the drag force. Its dimension is m times L divided by the t square. So the velocity, the dimension of velocity is L over t. And we know the dimension of the diameter, it should equals to L. Dimension of viscosity, it's m over L times t, right? And then in the second step, we determine the number of the pi group. So we have 4 variables here. And we have like 3 dimensions, which is M, L, and T, right? So the number of the pi group is 4 minus 1 equals to 1. So there is only one pi group. And the third step is to set up a table with 4 rows, which is the number of variables, right? And then the column of the table is also 4. It equals to the number of dimensions plus 1. Okay, so next step is to list the table. So I will put the table here. As I just mentioned, we have 4 rows. Second row. And we have 4 columns. Okay. So in the first row is the title of each column. So on the left hand side is variable. On the right hand side is dimension. So the first variable is the drag force. Its dimension is ml divided by t squared, we put here. And then the next one is the viscosity. Its dimension is m over l times t. The third one is the velocity. Its dimension is l over t. And last one is d. The diameter, its dimension is l, right? So, and then in the next step, we want to select d to eliminate l. So use all the variables to divide it, this like the parameter d here. So the second column will be Fn divided by d. So its dimension, we cancel l here, so it's m over t squared. For this case, it's mu divided by d. So it's this one, it should be like, because like l is here, it should be mu times d, right? So we use mu times d. It will be m over t. And this case is v divided by d, so it's 1 over t. And then we use the v divided b to eliminate t. So we divide this part by this part, right? So after that, we got Fn times d divided by b squared. So the dimension is m. And for this case, we divided this like mu d by the vd, which is mu times d squared over v here. Okay, so then we got its dimension is m. And then in the end, we use this one to eliminate m. Therefore, we can get Fn divided by mu times v times d. This part is dimensionless, so we put a 0 here. And then we can make a conclusion that we got the only one pi group. Which is pi equals to this one. It's Fn over mu times v times d. Okay, so we use the step-by-step method to solve this problem. We just use the step-by-step method to solve the problem 5. Now let's take a look at how should we use the exponent method to solve the same problem. Okay, so the first step is the same, which is to list all the dimension of each variable. So the dimension of the velocity is L over T, and dimension of diameter is L. Dimension of the viscosity is M over L times T, right? And then the second step is also the same. So we determine the number of pi groups. So we have 4 variables here, and there are 3 dimensions, which is L, T, and M. So the number of variable is 1. And then this step is different. So in this step, we form the product with dimensions. So which means the ML over T squared equals to, put it to the left hand side, put this stuff on the right hand side. So it's L over T to the power of A times L to the power of B, and then times M over L times T to the power of C. Because it's a dimensional homogeneity, so we equate powers of dimensions on each side. So for the dimension L, So on the left hand side is power, it equals to 1. On the right hand side is for this item, its power is A plus its power is B for the second item. For the C, it's because like this is minus, so we minus C, it equals to 1, because on the left hand side its power is 1. For the M, on the left hand side it also equals to 1. So for this one, it should be 0, 0, and the power is C here. And for the T, it should be -2 here. And this one, it should be -A, right? And this one, it doesn't have T here, it have a -C here. Okay. So we solve for exponents A, B, and C in the next step. So which is step 5. And then we know the C, it equals to 1. And A, because C, it equals 1, so A equals to 1, and B should also equals to 1, right? And then we write the dimensional equation with exponents. Variable drag force, it should equals to V times D times mu, which is viscosity. So its power is all equals to 1. We just solve it here, right? So we can make a conclusion that all there is one pi group. It equals to, if we put it to the right hand side, it equals to V times D times mu. Okay, so this is a result, like we use exponent method to solve this problem. Okay, so for the problem 6, we only use the step-by-step method as a demonstration. So in this problem, we know that the delta P over delta L should be a function of the viscosity, the mean velocity, and the diameter. It asks us to determine, like using the dimensional analysis to derive a functional relationship relating these variables. So the first step is to list all the dimension of each variable. So the dimension of viscosity is M over L times T. And dimension of velocity, it equals to L over T. Dimension of the diameter, it's L. And the dimension of delta P over delta L, it equals to M over L squared times T squared. Okay, so the next step, we determine the number of pi group, right? And we have like 4 variables, and we have 3 dimensions. So the number of pi group is 4 minus 3, which is 1. And then in the next step, we set up the groups. Set up the table. And we know the number of rows should equals to the number of variables, which is 4. So we will have 4 rows here, and the number of the columns, it equals to the number of dimension plus 1. So the number will be 3 plus 1, which is also 4. And then we set up our table here. And then we list the variables and primary dimensions in the first column. So for this one, it's delta P over delta L. It's M over L squared T squared. For the next one, it will be mu. It is M over L times T. And next one is velocity. It's L over T. Last one is diameter. It's L. The first step, we want to eliminate, select D to eliminate L here. So for this case, we need to times D, right? Because like L is here. So it equals to delta P over delta L times D squared. And then we have M over T squared. For this case, we also times D, which is M over T. For this case, L is here, so we use V divided by D. It's 1 over T. And then we select V over T to eliminate T here. So this one, T here, so this case, we got delta P over delta L times D to the power of 4. And then divided by the V squared. Corresponding dimension is M. Right? And then, like for this case, we use V over D times this item. Sorry, we use this one to divide it, this one, right? So after that, we will get mu times D squared divided by the velocity. And then we have its dimension is M. And then we want to eliminate M. So for the first item, we got delta P over delta L. It should times D to the power of 2 divided by the mu times V here. And then it's a dimensionless item. Okay, so finally, we will have one pi group, right? It equals to pi equals to this one is delta P over delta L times D to the power of 2 divided by mu times V. So this is the result for the problem 6 by using the step-by-step method. Now let's take a look at the last problem. In this problem, it said the velocity is believed to be a function of the fluid density and the particle density and the fluid viscosity, the particle diameter, and the gravitational acceleration. And it asks us to find the pi groups in the form of this. And we will solve this problem using the exponent method. So the first step is to list all the dimensions for each variable. So on the left-hand side, there is velocity. Its dimension is L/T. On the left-hand side is a density. Is M/L to the power of 3. So for the same is also the density, but is for the but is for the particle density. Sorry. So it equals to M/L to the power of 3. And then it is the viscosity. It's M/L times T. Dimension is L. Gravitational acceleration dimension it's L/T squared. Okay, so for this case, we do not need to identify the number of the pi groups. But if we want to identify, because we have 6 variables here, have 3 dimensions. So the number of pi group in this problem, it will be 6 minus 3. It equals to 3, right? And then we want to form the product with dimensions. So on the left-hand side is V here. So V to the power of A, it equals to the rho sub F to the power of B times the rho sub P to the power of C times mu to the power of D times D to the power of E times G to the power of F. And because it's dimensional homogeneity, so we equate the power of dimensions on these two sides. So on the left-hand side, so for this one, the V, it equals to dimension is L/T to the power of A. It equals to M/L to the power of 3, then to the power of B. Then times M/L to the power of 3 to the power of C, and times M/L times T to the power of D. And then for diameter, its dimension is L and to the power of E. Then times L/T squared to the power of F here. Okay. Then for each dimension, okay, so for the L, on the left-hand side, the power of L is A, right? So A, it should equals to, it's minus 3B minus 3C here. So L is minus D. And then we plus E. And then plus, here is L plus F. for m, on the left hand side it equals to 0, and this one it equals to b plus c plus d. For these two items there is no m, so it equals to 0. And for the t, on the left hand side equals to minus a, it equals to, there is no t, there is a t here, so it's minus d, and then is minus 2f. Okay, so we call this equation 1, and this one is equation 2. This is equation 3. From equation 2, if we put the c to the left hand side, so the c it equals to minus b minus d. For the third equation, we can get a it equals to d plus 2f, right? And then if we plus equation 1 with equation 3 here, okay. So we canceled a here, and we got 0 it equals to minus 3 times b minus 3 times c minus 2d plus e minus f. And then if we just reorganize this equation, we will get 3b plus 3c plus 3b minus 3c, okay, 3b plus 3c plus 2d minus e plus f. This should equals to 0, and we call it equation 4. If we bring equation 2 to equation 4, we will get, bring this one to this one, we will get e it equals to minus d plus f. If we bring this 3 equations to the original equation, then we will get is v to the power of a it equals to d plus 2f, and b here is, it doesn't change, so it's rho sub f to the power of b times c rho sub p. C equals to minus b minus d times mu here, mu to the power of d times capital D is like is d here is e to the power of e equals to minus d plus f times g is to the power of f. So after we collecting the items, we will get, on the left hand side, we put all the items have to the power of d together. So is v times rho sub p times diameter d divided by mu to the power of d. It should equals to g times d divided by v to the power of 2, then to the power of f, then times rho sub f over rho sub p to the power of b. Because like in this problem, it asks us to find the pi groups in this item, and we can compare this one with this one. So we can adjust our power here times minus 0.5 to have exactly the same format. But like meanwhile, after we do that, adjust the power here, we also need to adjust the power here. But it's unnecessary because in this format, we can already identify the pi 1 and pi 2. So this one is pi 1, and this one is pi 2. Okay, so therefore, the function can be written as v over square root of g times d. It should equals to the function of pi 1, which is v times rho sub p times d over mu, and pi 2 is rho sub f over rho sub p. Okay, this is the result for our last problem by applying the exponent method.